Welcome and thank you for joining. In this lesson, we will continue discussing the higher order derivatives applications. Oh, that was a long title. So, in simpler words, we're analyzing motions, so the position time graphs, and we're trying this time to analyze in more detail how to determine whether an object is speeding up or slowing down. So, in order to best explain this, I brought in a set of two graphs, or two sets of graphs. So the first set of graphs represents a speeding up motion and the second a slowing down motion. Now remember that the point of reference at all times will be when position is 0 and at time equals 0. So 0, 0. So point of reference is always right here at the origin. Now, you're probably wondering, well, how do I know this is speeding up? This is how I know. So the motion described in here is relationship between position and time in all these graphs, by the way. So this motion is described for the first 4 seconds or 4 units, right, in time. And what I'm going to do is I divide the time interval of 0 to 4 into 2 equal halves. So for the first 2 units of time, can be seconds, hours, we don't know, doesn't matter. Notice that the distance or the position is this much. That's how far the object has gone. But for the second time interval, look at how far the object goes. So a lot further. So you can agree with me that this is smaller than this one. So which means that with time, and remember that we read graphs left to right, just like we read books in English, with time, the object has gone a further distance, okay? So that's how I know that this has been going faster with time. Similarly here, for the first half of the time interval, look at how far the object goes, this far. And for the second half, this is how far it goes. So when you read the graph left to right, then you're going to say, oh, so first 2.5 seconds, this is how far it goes. But second half of the time interval here described in here, it goes further. So these are speeding up motions. Now, in a similar way, we explain the slowing down. So again, here we have the first 4 seconds, the object goes this far. And for the second half of the time interval, it goes this far. So which means that initially it goes a further distance for half of the time and then not as far for the second half of the time, which means that the object is slowing down. Similar to this, so we are right here is the first half of the interval, the time interval. You see that the object has gone far from 5 units, so 3.5. But for the second time interval, the object doesn't go as fast. So that's a slowing down motion. That's how we explain it, as if we were, I don't know, in elementary school, right? And we were to, let's say, for example, read the graphs or understand the graphs. But now we are in grade 12 and we're doing calculus, and we'll explain this a little bit more differently and in a more sophisticated fashion. Just kidding. So it's simple, it's easy. So in order to analyze the speeding up and slowing down motions, we look into velocity and acceleration. So when you look at the first graph here, velocity, which is the first derivative of position or the slope of the tangent of the position time graph, is all positive. I noticed that all the tangents I draw here have positive slope. So we're going to say that velocity is positive. Now let's take a closer look at velocity. Yes, it's positive here at the beginning of the motion, but it becomes more positive and even more positive here. That tells us that velocity is increasing in value. That means that the rate of change of velocity is positive. And when we say rate of change of velocity, v prime, isn't that the same thing as if saying acceleration? So we're going to say both velocity and acceleration are positive. Now let's take a look at the second graph. So velocity is slope of the tangent of position. You notice that slope of the tangent negative everywhere. So I'm going to say velocity, you're negative. I can tell. I can see from the graph. And now let's take another closer look at velocity. So negative, more negative, even more negative. That means that velocity is becoming more and more negative. So the rate of change of it is, guess what? Negative, which means that acceleration is negative. Now, we know these are speeding up processes. And now we're going to look into the signs of velocity and acceleration. Is there a relationship between them? As you can see, in the first graph, they were both positive, second graph, both negative. So what they have in common is that if you multiplied velocity with acceleration, in both cases, we'll get a positive product. How? Because acceleration positive and velocity positive multiplied give a positive. Acceleration negative and velocity negative will give a negative, positive. Goodness. So we're going to say that to determine whether an object is speeding up or slowing down for that matter, we need to identify or determine the sign of the product, velocity, acceleration. And if it's positive, we can tell for sure and we can say for sure that the object is speeding up. Now, how about slowing down? So we analyze the slowing down motions in a similar way as speeding up, exact same way I should say. So we study the sign of velocity. Look at velocity here, slope of tangent, positive. So we're going to say that's a positive. Let's go purple this time. And let's take a closer look at velocity. So positive, less positive, less positive, becoming zero. That means velocity is decreasing. Rate of change of velocity negative. And then acceleration is negative. So we're going to say rate of change of velocity or acceleration is negative. Now, let's take a look at the second graph. Let's see what happens to velocity here. It's negative, negative, oh, negative everywhere. So velocity is negative, and we can do nothing about it. That's the way it is. Now, let's take a closer look at it. So we have negative, less negative, even less negative, about to become zero. So when a quantity goes from negative to zero, it means that quantity is increasing. So the rate of change of velocity is an increasing rate of change, or should we say a positive rate of change, which makes the acceleration positive. Now, lastly, we're going to study the signs of velocity and acceleration. So if you were to multiply them, you would be multiplying acceleration, which is negative right here, with velocity, which is positive right there, right? So minus and a plus will give a minus. Now let's take a look at this one. Acceleration is positive, velocity is negative. So here we have the product of a positive with a negative, so the product will be negative. So what velocity and acceleration have in common in this case is that the product, velocity, acceleration, in a slowing down process is negative. So in summary, we're going to say that an object is speeding up when the product velocity and acceleration is positive. I'm just going to write positive like this, so or bigger than zero. And an object is slowing down when velocity and acceleration have a negative product. So when can a product be positive? When either velocity or when both velocity and acceleration are positive, or when both velocity and acceleration are negative. So they're going in the same direction in a way. An object is slowing down when velocity and acceleration have opposite signs. So velocity positive but acceleration negative, or velocity negative and acceleration is positive. So if you want to actually look at an example in here, then we can continue with the cheetah's example. So we have to find the acceleration or we have to find the acceleration at any time t when we're given the position function. So that means that we need to find the first derivative, which is basically the velocity function. And in this case, it would be equal to, remember this is the equation of position, so that must be differentiated, negative 3t squared minus 30t, and then plus 63. So therefore, we'll say that the acceleration will be the first derivative of velocity or the second derivative of position, same thing. So in our case then we'll have the derivative of 3t squared is equal to 6t, and derivative of negative 30t is negative 30. So acceleration, everyone, velocity, everyone. I'm just going to write them down because I'm pretty sure we'll have to use them in the next questions. So next, we are asked to find when is the acceleration 0. So why do we have to do this? If we're about to find the speeding up or determine or analyze speeding up, slowing down motions, we need to study the signs of acceleration and velocity. And to study the sign of a function, we need to know where the zeros of a function are, because the zeros will always separate the positives from negatives, so they're the guiding points. So acceleration will be 0 whenever at equals 6t minus 30 becomes 0. So 6t minus 30 equals 0 whenever t equals 30 over 6, which will make acceleration equal to 0 at 5 seconds. So now we have to find the intervals when acceleration is positive and when it is negative. So for this, we build a very simple chart. Actually, we don't really need a complicated chart because acceleration is just some linear function here. Very easy to analyze. But remember, time will start at 0 and we have a key value of 5 in here. We can go to infinity, but I'll place infinity here because we haven't been given any restrictions. So this is a linear that goes up because the slope is positive, which means that once it passes the 0, it goes from negative to positive here, right? So that means between 0 and 5 is negative, and 5 to infinity positive, and right at 5 is 0. So we're going to say that the acceleration will be positive for the time interval from 5 to infinity, and it will be negative within the time interval from 0 to 5. Now we need to find the intervals when the theta is speeding up or slowing down. And for this, we're going to ask for help the velocity zeros. So 3, and then we have t squared minus 10t plus 63 divided by 3, it's 21. In factored form, that's 3t minus 7, t minus 3. So the zeros of velocity are at 3 and 7. So we have the key values of velocity, 3 and 7, and they will go right here on the number line. So for velocity, we have the key values at t equals 3 and 7, we said. And for acceleration, we have the key values at 5. So 3, 5, and 7 are all going down on this number line in order from lowest to highest. And the scale doesn't matter, as always, right? You remember that. So we're going to start off with the factors of velocity. So we have t minus 7, t minus 3, and here we have the sign of velocity, which is the product of, it has actually a factor of 3. I'm going to list that in there. It's important too, just in case the factor is, the numerical factor is, here it's a negative, so we always have to include the numerical factors as well. And next we are going to list the sign of acceleration. So acceleration is only one factor, linear factor, and that was 6t minus 30. So 6t minus 30. So that would be the sign of acceleration. And down here, we are going to write the sign of the product. So sign of velocity with acceleration. And based on that, we will be able to describe the motion. So description of the motion. Perfect. So I'm going to start off by dropping some perpendiculars from the zeros. all the way down here. I'm going to make them actually in blue. Okay, and we have the zeros of t minus 7 here at 7, so I'm going to write that down. The 0 of t minus 3 is at 3, and that will make 0 the velocity. Now for acceleration, we have the 0 of acceleration at 5, so 0 right here. So wherever velocity and acceleration is 0, then the product will be 0 as well. So I'm going to make this nice bright red. 0, 0, 0. So let's study the sign of every factor, each and every factor. So we have t minus 7 will be negative for any value less than 7, positive after this. Again, the explanation is the same. I keep repeating in every example. So t minus 7 is linear positive leading coefficient. This is the 0. That means the line goes up. So start negative and positive. So negative, negative, negative. After the 0, positive. T minus 3, same idea. Positive leading coefficient, linear function starts negative. After the 0, all positive. So we're going to say that velocity will be the product of two negatives, a positive, a negative with a positive, a negative with a positive, a negative, two positives, a positive. There goes the velocity everywhere. Now we'll do acceleration. So what we have in here is, again, a linear function with 0 at 5. So starts low and go high. So that means that acceleration here is negative, negative, positive, positive. So now we're going to marry these signs together. So that sounds fancy. So we have a plus for velocity, a minus, a plus. Okay, all right. And now we have the minuses. So a minus, the acceleration, the minus, but it does start with a minus. To my defense. Here we go. Minus, plus, and plus. So if we multiply a minus with a plus, then we get a minus. Two minuses, we get a plus. And then, let's make this perfect. A minus with a plus, a minus. Two pluses, a plus. So here go our signs. Minus, plus. So whenever the sign velocity acceleration is negative, the object is slowing down. When positive, speed up. Negative again, slow down. And positive, speed up. And with this, we understand now, or we have found, the intervals of time when the object is speeding up or slowing down. So the object is slowing down in the time interval 0 to 3 and 5, 7. So we'll write that down. Sometimes this would be a question on a test. So slow down in the time intervals from 0 to 3, joined by 5 to 7. And it is speeding up in the time intervals from 3 to 5 and from 7 to infinity. We all know that's a lie. We don't continue the motions to infinity. Living things don't, at least. But it's just a math problem. Normally we would have restrictions somewhere in here. I hope this made sense. I hope you find learning entertaining and fun, because learning is fun. Bye for now.